In this video, we're going to introduce exponential expressions and talk about a lot of properties that we're going to find really useful when it comes to working with exponential expressions algebraically. So first of all, when we say that we're looking at an exponential expression, what are we talking about? Well, we're talking about something that looks like this. B raised to the power of n. So we call B the base and n is the exponent. So the first thing to note is when we do something like this, let's look at this one, 4 to the fifth. That does not mean 4 times 5. What it means is that I am multiplying together 5 factors of 4, right? Or 4 times 4 times 4 times 4 times 4. All right, so that's what it means. So resist the temptation to, say, oh, 4 and a 5, okay, that's 20. No, this is not multiplication of these two numbers. It's telling you how many times we're multiplying the base together. All right. One of the things that is important to not gloss over here is how we work with our calculator when it comes to exponents. So using Desmos here, um, if you want to take a number raised to the second power, which is probably the exponent that you're going to use most often, you can just click that number, let's say 6 raised to the second power. 6, and then you hit this little button here to put a 2 in the exponent. And of course, that equals 36 because it means 6 times 6, which would give us 36. To enter something like the one on our notes here, 4 to the fifth, you're going to use this button instead. So you first type the 4, whatever your base is, then type this, and then the cursor, notice, goes up into the exponent, and so then you tell it what exponent you want. So 4 to the fifth, and so you can see that that's equal to 1024, which is exactly what you get when you multiply 4 times 4 times 4 times 4 times 4. All right. The other thing I want to just really make a careful note of is when you are raising negatives to powers, pay attention to how many negatives are involved, and whether that negative is in parentheses or not. All right. So if you take a -2 in parentheses and raise it to the fourth power, then that's literally -2 times -2 times -2 times -2. And since there's four negatives all being multiplied together, you'd get +16. However, if that negative was not inside of that parentheses, then the exponent of 4 only applies to the 2, and the negative's just along for the ride. So you can kind of think of that negative just kind of hangs out front, and then it's just the number 2 that gets multiplied 4 times, resulting in -16. So just pay attention to whether a negative's in parentheses or not. At the same time, just because a negative's in parentheses does not necessarily mean that it's going to end up being a positive answer. So for example, if I did -2 to the third, well, that would be -2 times -2 times -2. Those two would multiply to make +4, and then those would multiply to make -8. So in that case, even though the negative's in parentheses, you get a negative still. But the point being that if the negative's in parentheses, then it needs to be the thing that's being repeatedly multiplied, which has the potential of being a positive answer or a negative answer. All right, so let's run through some examples here. A lot of these really are kind of just calculator problems, but it's also important to understand it beyond the calculator because sometimes the calculator doesn't give you nice numbers. So if you typed 3 to the fourth into the calculator, as I showed you on the previous page, that would give you a nice number, right? It's 3 times 3 times 3 times 3, and it would give you the number 81. No problem. All right. Now, -5 squared, here's where it's important to understand that you really are multiplying -5 times -5, which would give you +25. Now, your calculator is smart and knows that if you do put parentheses, let's say you go ahead and put -5 in parentheses and then you square it, notice it tells you it's +25. Whereas part C up here, if you don't put the parentheses there, then it will be negative 25, as you can see. Okay. Now, part D is one where you really do need to make sure that you're understanding what's going on here because 2/3 is not a nice number, right? It's 0.66666 on forever. So this is where it'd be important to say, you know what, I'm doing 2/3 times 2/3, which would give me 4/9. Here's another thing to just make a note of. Um, in an earlier, let's see, in an earlier math class, you would have studied order of operations, PEMDAS. And so in the order of operations, you might remember that E stands for exponent and multiple M stands for multiplication. So exponents always come before multiplication. So if you were working this problem out, the first thing you would do would be to say, what's 6 to the second power? Of course, that's 36. And then after that, you multiply 5 times 36 and get 180. Okay. If you multiplied the 5 and the 6 first, you'd get a completely different answer there. And then something like zero point 0.2 to the second, if you take zero point 0.2 times zero point 0.2, while we're not really into manual arithmetic in this class at all, it's just worth remembering the trick that when you're multiplying decimals, just multiply the numerical parts, really disregarding the decimals for a moment. So I know 2 times 2 is 4, but then you count how many place values are there to the right of the decimal point. There's one here and one here. So that means you're going to send the decimal point back 2 places. So the answer is 0.04. Of course, a calculator can help you with that, but I just wanted to remind you of that little rule. All right, so what we're going to do over the next number of slides is we're going to, the next number of pages in your notes is talk about some specific exponent rules that we're going to use throughout this quarter. The first one is that if you are multiplying two exponential expressions together and their bases are the same, then what you can do is actually add the exponents in order to simplify. So a to the m times a to the n is a to the m plus n. You add them. And the reason you can see this is if you were to take something like x to the fifth times x to the third and write out all how many x's are multiplied together, well, there would be 5x's here multiplied by 3x's here. Well, that's a total of 8x's. So I literally just added the number of x factors in the first one and the number in the second one together to make my resulting x to the eighth power. So pretty straightforward when you actually write it out like that. So that allows us to make quick work of some things. So for example, 2 to the fourth times 2 to the second is 2 to the 4 plus 2, which would be 2 to the sixth. And of course, 2 to the sixth is something I can just punch in my calculator and get 64. When you see something like this, remember that if there's no exponent showing, there is still an exponent there. It's just a 1. So x to the first times x to the 23rd is x to the 1 plus 23. So x to the 24th. And then even though the rule isn't written out to encompass 3 different factors multiplied together that have the same base, it doesn't take a huge leap of logic to say, well, you know what? Probably I can go ahead and just add up all the exponents. So s to the 11th power is how I would simplify that. All right. So with that rule in mind, right, that if I multiply like bases, I can add the exponents. Let's simplify some of these. All right. And I'd encourage you to press pause, try these yourself. They're a little more complicated than the ones we just did. But using some of your knowledge you came in with of different ways that you could manipulate expressions, maybe pause and give them a try, and then unpause and you'll see what my solution is to these. All right, so on the first one here, I see that I have an x squared and an x to the ninth, so like bases. So I want to be able to add those exponents. But I've got this 4 and -3 hanging out. But the thing we want to remember is that we can multiply in any order we want. So I can just switch the order of multiplication to put the numbers next to each other and then the the variable factors next to each other. So of course, 4 times -3 is -12. And then x to the 2 plus 9. So x -12 times x to the 11th. That would be my simplified version of that expression. All right, here I've got m to the 5th times m, n to the 10th times n to the 8th. Okay, so only like bases can be combined by adding their exponents. So put the like bases together, and let's remember that that m is the same as m to the 1. So just reordering. So m to the 5 plus 1 times n to the 10 plus 8. So m to the 6th times n to the 18th. Oops. And then finally, this last one, if it helps you, remember that if there's a negative out here, remember that's the same as -1 times x to the ninth times y, right? Times 4 times x squared times y to the 11th. And so I'm really putting together -1 times 4 when I put the numerical parts next to each other. And x to the ninth times x squared, y to the 1 times y to the 11th. So -4 x to the 11th, y to the 12th. All right, so those are us just, using the commutative property of multiplication that says I can multiply in any order I'd like, and then using the rule that if I'm multiplying like bases, then I can add the exponents. All right, but that's not the only rule. We also have one for what does it look like when we raise a power to a power? So literally taking x to the third raised to the fourth power. Well, what does that do? Well, if I write this out, it would be x to the third multiplied 4 times, right? But then each of those x to the thirds becomes x times x times x. So you can easily see that there's a total of 12 x's multiplied together. But what we've done is we've made groups of factors of, or groups of 3 factors, and then there's 4 of those. So 4 times 3 is 12. So that means that when you have a power raised to a power, all you're going to do is you're going to multiply the two exponents together. All right. So in these examples, this just becomes y to the fourth to the 10th becomes y to the 4 times 10. So y to the 40th. Z to the 6th to the third is z to the 6 times 3. So z to the 18th. And then -2 to the third to the second would be -2 to the 3 times 2, which would be -2 to the 6th, which would be +64. Again, this is one of those where we're repeatedly multiplying -2, but because I'm multiplying an even number of negatives, becomes positive. Another rule that we can utilize. Suppose I take two different bases raised to the same power. So the two different bases are being multiplied and they're both being raised to the fourth. What you can do then is you could rewrite it as a times b times itself times itself times itself. But then because we know that multiplication is commutative and we can write things in any order we'd like, we could put all the a's first, right? 4 of those, and all the b's second, 4 of those, which would just be a to the fourth times b to the fourth. So the result of that is if you have two things multiplied and you raise them to the same power, then you can individually raise them to that power and then multiply after that. So in part A, that means I can take x to the seventh times y to the seventh. In part B, I can take 3 to the fourth times y to the fourth. But if you do something like that, use the fact that 3 to the fourth is something you can easily compute. So 3 to the fourth, and again, remember if you need your calculator for help, you are not taking 3 times 4, right? Don't fall into that trap. You are taking 3 raised to the fourth power to give you 81. So 81 y to the fourth is the simplified version of that. And then that last one, let's be real careful here. Um, you're applying this 2 to everything, okay? Including the negative 2. So don't just raise 2 to the second power and turn it into 4 immediately. Write it out like this: negative 2 to the second power times p to the fourth to the second power times q to the third to the second power times r to the second power. So I've taken each of the factors and raised them to the second power. And hopefully you're okay with that. They don't write it this way just to keep it concise, but like, I don't think you would probably be too upset if I said that because this is true, this is also true. So in other words, if we had more things than just a times b, they could all be raised to the nth power if we're multiplying. So that's what I employed there. Now, the negative 2 to the second, I know that's positive 4. These two, the p to the fourth to the second and the q to the third to the second, that's another opportunity for me to use another exponent law. So just a couple slides back, right? We learned what to do with that. A power raised to a power means I'm multiplying my exponents together. So p to the 4 times 2, q to the 3 times 2. So my final simplified version here would be 4p to the 8th, q to the 6th, r squared. All right. Now, if this is true when you are multiplying two things and raising them to the same power, then you can bet it works the same way if you happen to be dividing two things and you raise them to the same power. So if you have a over c raised to the n, then that can be a to the n over c to the n. All right. So we'll just do one example on this one, but I'll take it just kind of one step at a time. So what you want to think about here is in this example, think about the top, the 5x to the sixth, that's like my a, and the 9y cubed, that's like my c. And so what we can say is that, let me just switch colors here. What we can say is that for starters, it is 5x to the sixth to the second power, my a to the second power, over 9y cubed to the second power, so my c to the second power. But then my next step in this process is to use the rule from the previous page. I'm multiplying 5 times x to the sixth. So I know that it's okay for me to do this. Put the exponent of 2 on each of those individually and on each of these individually. That was a y, not an x, sorry. And then we can go ahead and calculate 5 squared is 25. But in the case of x to the sixth to the second power, that's one where we should be multiplying the exponents. So 25x to the 12th over 81 y to the 6th. All right. So lots of rules being thrown at us. I'm on a slide in a moment. I'm going to summarize all these because I know it's a lot that we're all throwing at ourselves here all at once, and then there'll be a chance to kind of put them all together in some practice questions. But one more here. We talked about what happens if I multiply like bases. Well, we discovered that if we multiply like bases, we end up adding the exponents. So if we divide like bases, then this might stand to reason that we would subtract exponents, and that's exactly what we do. Because look at this. If I have x to the eighth, that means there's 8x's multiplied on top. X to the third, there's 3x's multiplied on bottom. Well, you're going to literally take away three of those from the top because you have those same three factors on bottom and you're canceling them out. So it would be x times x times x times x times x is x to the fifth. So we just end up subtracting. So in something like part A, we simplify it like that. Something like part B, we simplify it like that. But of course, if you're working with numbers, go ahead and pull out your calculator. Negative 3 times negative 3 is positive 9. And then on this one, what you can see is that even if you have multiple different bases within the same expression, you can kind of just treat each part like its own individual, kind of own individual piece. And maybe what I'll do here is just say, let me write bigger and provide more space like that. And so what we could pretty much do here is just say, it's like three little individual problems that are all multiplying together, right? So just kind of take it one at a time. So if you take 8 divided by 4, well, we can do that. 8 divided by 4, no exponent law is needed there. That's just 2, right? And a 2 on top, right? But then this exponent law says if I have 8 to the third divided by 8 to the second, we'll do 8 to the 3 minus 2, and b to the ninth over b to the sixth, b to the 9 minus 6. So we'll have 2a b to the third power. One last law here. It's kind of an interesting one. Any number besides 0, if you raise it to the 0 power, you're always going to get 1. Okay. So that means, 5 to the 0 equals 1. It means that 17 to the 0 equals 1. It means that 323 divided by 876 to the 0 is equal to 1. Okay. So the reason that's the case is on the one hand, if you take a to the m divided by a to the m, that's something divided by itself. So of course you should get 1 as an answer. But on the other hand, because we know that dividing like bases means you subtract the exponents, that would be a to the m minus m would be a to the 0. So these two things have to be the same. So that's another exponent rule to have in our back pocket. Now, you're hopefully following along with the notes here. The thing on the next slide is not at this stage of your notes. What you can do is move forward a few pages and you'll see a summary of exponent rules, but there'll be a few more. So there'll be these 6 that I've got written here on the slide, and then there's a few more. So what's going on is there's a few more exponent properties that I'm going to introduce in a separate video, and you'll use those for um, for a later homework assignment. But these six are sufficient for your first homework assignment on exponent rules. So just know that even though we haven't done uh, a couple of pages that are between where we're at right now in the notes and these rules, as you're doing the homework, go ahead and flip to that page in the notes that has these rules and go ahead and use those as you work through problems. Okay. So speaking of that, with these six, armed with these six rules in our tool belt, there's six different questions where I want you to simplify the expression given as much as you can. And so they're on the next two slides. So here, A, B, C, and then here, D, E, F. So this is one where I definitely want you to hit pause, try your best on all six of them, and then go ahead and unpause and see how I go about it. All right. So assuming you're coming back to me right now, after working through these, I'll just kind of work through these myself. Um, so in part A, um, and by the way, I'm going to show all the detail. Um, So if there's like a little step that maybe you did two steps in one, that's likely okay as long as I can follow your work. But I'm going to really kind of be careful here. So first of all, I've got division and they're raised to the fourth power. So that means I can take the top to the fourth and the bottom to the fourth. But then I have multiplication raised to the fourth. So I can take the x to the fourth and the y to the fourth separately. So this is what I mean by it might be okay that you skip some steps. If you kind of combine those two and went straight here, that's okay. I don't mind that at all. All right, 3 to the fourth is 81. And I don't think there's really anything else I can do with my x to the fourth and y to the fourth. So I'm going to leave it just like that. All right, part B. All right, so here's one where I'm multiplying a bunch of things, multiplying more than two things, but as we saw earlier, that's okay. The rule where I can take each factor raised to that shared power applies if there's more than two as well. So 7 to the second is 49. And then now we apply our power raised to a power rule. So 49, x to the 8th, y to the 20th. And here's another in part C. So I will take the top raised to the fourth, and I'll take the bottom raised to the fourth. But on top, I've got more than one thing multiplied together in parentheses raised to the fourth power. So I'll put the 4 to each of those individually. And then negative 2 to the fourth, that's something I can compute, right? Use my calculator or in my head, that's fine too, to get positive 16. And then use the power raised to a power means I am multiplying the exponents. So my final answer there would be 16 x to the 20th over c to the 16th. All right, so the ones here on part D, this is one where I did this on an earlier problem where I kind of gave myself a little bit more space so that it was really clear that we've really just got two separate fractions here, right? So we've got this one and we've got this one. We can just treat them separately. So I'm dividing like bases. And so we know that when we divide like bases, we are subtracting our exponents. So x to the 10 minus 6 and y to the 9 minus 8. Of course, y to the 1. And anytime you get something like y to the 1 as an answer, please drop the 1, right? Y to the first power is just y. All right, part E, this is a chance for us to use the rule we just learned last, which was anything to the 0 power is just going to be 1. So that changes to a 1. That changes 3 to the third is 27. So just get 28, just a numerical answer on part E. All right, and then finally, 2a squared b to the fourth all over 3y to the fourth. But then I have all this multiplication on top. I have multiplication on bottom. So then every single factor can be raised to the fourth power. And then 2 to the fourth and 3 to the fourth, I can compute those, 16 and 81. And then I'm going to multiply the 2 and the 4 to give a final answer of 16 a to the 8th b to the 4th all over 81 y to the 4th. Now, this is just a good chance for me to point out kind of, once again, that I'm showing a lot of detail here. So here's kind of a good example of where you could probably cut your steps in half. If you understood that whether it's multiplying or dividing, every factor gets a power of 4, I think it's just fine. Oh, I didn't want to cover that exponent. Sorry. Let me try that again. So if I circle this step here, going directly from here to here, and then just going directly from here to here without showing the 2 times 4 in the a, but just saying, oh, okay, I'm going to multiply those and make those a to the 8th. So just having those 3 steps, that's enough, right? So I'm just trying to be very clear about where everything's coming from, but I'm not suggesting that you have to just kind of show a ridiculous amount of steps. You just do whatever's comfortable for you, all right?